So far in your math careers, complex numbers have lived largely in the algebraic world. We've been adding, subtracting, multiplying, and dividing because we want to solve a polynomial, or simplify an expression. However, with the complex plane, the entire complex world can be represented graphically, and therefore geometrically. Through this, we can visualize the operations we've already been doing, and also look at some new ones we haven't done. Now, most textbooks will just kind of dump these operations on you as formulas to memorize rather than even showing their visual aspect.
I'm looking at you, Michael Sullivan!
Considering the many mathematical and practical uses of complex numbers, as well as the numerous advantages of the complex plane, it's strange that textbooks don't teach this sooner. Anyways, this is going to be a very lit topic, so let's go. To start, let's first see how to graph points on the complex plane. Instead of x and y axes like we're used to, we're going to use the axes real and imaginary. Let's plot the complex number 3 plus 2i. We'll do this based on its real and imaginary parts. So, we count 3 units to the right, then 2 units up, and there's our point. Just like in the regular Cartesian plane, the one with the x and y axes, any change in the real part of this number will change its horizontal position, and any change in the imaginary part will change its vertical position. The origin of the complex plane is 0 plus 0i, or just 0. The real axis lies on all points where the imaginary part equals 0, which makes sense. If a number has no imaginary part, then it must be real. Similarly, the imaginary axis lies on all points where the real part equals 0. If a number doesn't have a real part, it must be imaginary. And of course, all points on the complex plane are complex numbers. So the best way to learn is by doing. Pause the video and try to plot these points on the complex plane. This is pretty simple, so don't overthink it. I'll wait. Alright, here are the answers. I pulled a little sneaky on you in this problem, but that's how complex plane works. Now, for the purpose of visualization, it might be helpful to convert complex numbers into their quote-unquote polar form. Here are the equations for finding the polar equivalents of Cartesian points. X equals r cosine theta and y equals r sine theta, where r is the radius of the point and theta is the angle of that point from the positive x-axis. Well, the complex's real axis is the same as the Cartesian x-axis, and the imaginary axis is the same as the Cartesian y-axis. So z would be equal to r cosine theta plus I r sine theta. We can factor out the r, and our result, r times cosine theta plus I sine theta, is what you'll see in most textbooks. The same textbooks that don't use this information to visually show you what the heck you're doing when you're working with complex numbers. Come on guys, throw in some images in your slides! Anyways, this is how you get the polar form of a complex number, which will allow us to define a complex number by its distance from the origin and its angle from the real axis. Okay, so remember the whole reason we're doing this is because we want to see what happens when we add or multiply points together. Good luck trying to multiply your regular old ordered pairs. Now, let's get to operations in the complex plane. Alright, so welcome to the complex plane. Let's just take a random point. We can just plot a random point, and here we can see its x and y position, right? Its real and imaginary component, as well as its magnitude and its angle from the positive real axis. Now let's just take 2 points and add them together. What have we got? Well, we've got this random boy. So, 2 ways of looking at this, right? Maybe the more algebraic way is to take this point and separate it into its real and imaginary components, and then taking this point, separating it into its real and imaginary components, and then you can take this and add those together to get the real component of your sum, and then take these 2 bad boys and sum them together, and that will give you the imaginary component of your sum. But there's also the more geometric way. If we were to take this line and translate it over here, then we'd get this, and it would exactly touch this point and this point. And same thing if we were to take this line, move it up here, then it would touch this point and then this point, right? And that's kind of a visual way of adding them together, right? So if we have the complex numbers a, b, and c, right? Well, we took a plus b, and we got c. So logically, it would follow that b plus a would also equal c. So that's a visual way of representing the commutative property of addition. And a similar thing goes on with subtraction. So let's just take 2 points. All I'm going to do is subtract this point from this point. And so we get this. So we can look at this algebraically. We can take this real component and this real component and subtract this from this to get something like this, and that would give us the real component of our difference. We could also take the imaginary component of this point and the imaginary component of this point and subtract it like so, and that'll give us our imaginary component of our difference. And we could do the same visual representation as well. So if we take the complex number that's being subtracted, and instead of shifting it over to our second point, we're going to shift it over to our difference, and that's going to make the line between here and here. And if a minus b equals c, then c plus a equals b. So if we shift this line over here, then we can get the same thing as we did before. So addition, subtraction, not much to see in the way of complex plane. Multiplication's where it's going to start to get interesting. So let's just pick 2 random points, sure, and multiply them together. And you can see we've got this just random number, -1 plus 8i, right? And of course, algebraically, you could FOIL these two. You could distribute this and find the answer that way. But where's the fun in that? We're here to see the complex plane in action. So that's exactly what we're going to do. So to get this product graphically, what you need to do is add the angles and multiply the magnitudes. What the heck does that mean? Well, it means that when I have these 2 points, they also have these 2 angles. And all you have to do is add those 2 angles together to get something like this, and that'll give you the angle of your product. And then for magnitudes, we can use the Pythagorean theorem to find the magnitudes of these 2 bad boys. So this is 1 and 2, so it's 1 squared plus 2 squared, which is 1 plus 4. So this is going to be the square root of 5. And with this bad boy, it's going to be 3 and 2. So 3 squared plus 2 squared is 9 plus 4, so this is going to be the square root of 13. And then all we need to do is multiply these two, the square root of 5 and the square root of 13, and that's going to give us this magnitude. So the square root of 5 times the square root of 13 is going to equal the square root of 5 times 13, which of course is going to be equal to the square root of 65. And that's going to be about 8.1. And if you were to measure this with your unit ruler, it would also be about 8.1, but it would be exactly the square root of 65. So that's multiplication in the complex plane. It's really kind of visual. You just add the angles together and then multiply the magnitudes together, and that's how you get the angle and magnitude of your product. And with that information, you can find the exact point. It's going to be a similar thing with division. So if I just take 2 random points and divide, well then, what have we got here? Well, we're just going to do the inverse operation of what we did for multiplication. So we take this angle and we're going to subtract this angle by this angle. So we just go backwards here, and that's how you get this angle. And now we have our 2 magnitudes, so this is 4 and 5. So that's 4 squared plus 5 squared, 16 plus 25, which is square root of 41. And then this bad boy is 3 and 2. So that's 3 squared plus 2 squared. It's going to be the square root of 13 again. And so this magnitude right here, the little blue line that I've now covered up in a bunch of purple ink, is going to be the square root of 41 over 13. And that's going to be about 1.8. So if you can see roughly, this is about 1.8 units long. So when you're looking at the formulas for finding the product or quotient of two complex numbers, remember that that's all the formula is doing. It's multiplying or dividing the magnitudes and adding or subtracting the angles depending on whether you're multiplying or dividing. So now we get to a nicer visual aspect. So if we take this point, we're all familiar with the complex conjugate, right? It's your real part and then you subtract the imaginary part. So you'd get this point. So these points are complex conjugates. And a special property of complex conjugates is when you multiply them together, you get a real number. That property is very useful for something like rationalizing the denominator, which is just about the most algebraic thing you can do. But hopefully you can see why the complex conjugate does what it does. So if we call this angle theta, well then this angle is going to be negative theta. And so when you multiply these two together, you're going to add theta and negative theta, which is going to give you 0. And since the angle 0 is right on the real axis, it's going to give you a real number. So that's the 4 operations in the complex plane shown visually, rather than algebraically. But what about exponents, huh? What about the roots? Alright, let's get to exponents. Let's just pick a random point, select it twice, and multiply it by itself. So if we call this number z, and by the way, if you see a variable called z, it's generally implied that that will be a complex variable. Well, if we multiply z by z, then we're going to get z squared. And if we multiply z and z squared, then we're going to get z cubed. And then if we multiply z and z cubed, we're going to get z to the 4th. And this continues on with z to the 5th, and z to the 6th, and z to the 7th, and z to the 8th, and z to the 9th, and z to the 10th, and this is getting pretty crazy. You can see really easily the pattern. It's making a nice spiral, and hopefully it should be clear why that's the case. If we have this point, and it's got an angle, well, if we multiply it by itself, we're really just adding this angle to itself. So it's gonna add this angle to itself for z squared, and then add that angle to that angle to that angle for z cubed. It's gonna add it 4 times for z to the 4th, and then 5 times for z to the 5th. And now the magnitude. So if you see, this magnitude is greater than 1. So every time you multiply by itself, it's gonna get bigger and bigger and bigger. And so it's going to make a spiral outwards. That's a really neat result of just multiplying a number by itself a bunch of times. But now, what if the number has a magnitude less than 1, right? Something like this. If we multiply it by itself, well, we're going to get the same angle thing. It's going to spiral, but now, since it's multiplied by a number less than 1 over and over again, the magnitude is going to get smaller and smaller until it's very close to 0. So let's just start a circle, right? And if we put a point here, we know that this has a magnitude of 1, since it's on the circle, and this circle has a radius of 1. So if we take this number, multiply it by itself, well, since for the magnitude we're just multiplying 1 by itself, it's going to get 1. And so all of these points have a magnitude of 1, and we just multiply 1 by 1 by 1 by 1 over and over again. So our magnitude is going to stay at 1. Okay, so this result from finding the powers of a complex number is exactly the main idea for de Moivre's theorem, created by my guy, Abraham de Moivre. So if you take a complex number to a certain power n, then you multiply the magnitude by itself n times, in other words, raise it to the power n, to find the magnitude of the new point, and then take the angle and add it to itself n times, or multiply it by n, to get the new angle for your power. So when broken down like that, de Moivre's theorem is actually quite simple. So, as we all know, Michael Sullivan is trying to feed you lies, and he says that n can only be a positive integer. And that is extremely false. So here I have a point, and it's 1/2. So we're going to just take a random point, and we're going to raise it to the 1/2 power. In other words, take the square root of this number. And you see it's going to give us just a random number, right? But when we multiply this number by itself, we're going to get that number, which means that the formula worked for the square root, right? It worked when n equals 1/2. It'll work when n equals -1. It'll work when it's -4. It'll work when it's pi, right? It works for any real number n, not just the positive integers. Although, keep in mind, I only have the 5th edition of the textbook, and I have no idea whether he made this mistake in future editions. He probably already fixed it. Okay, so that leads nicely into roots. So let's just take a random point, and we're gonna get the point 2, and so we're gonna take the square root of this number when I press this button. And you can see it's giving us 2 results, which is strange, right? So let's just, I mean, this one looks closer, right? So if we multiply it by itself, yep, we get that point. And if we multiply this by itself, then we also get that point. So what's going on here? Well, when we ask, what's the square root of this complex number right here, what we're really asking is x squared equals this point. Solve for x. And since that is a polynomial with degree 2, it's going to have exactly 2 solutions, although both of them are in the complex world. So both of these points, if we draw a circle, they both have the same magnitude, but they're 180 degrees apart. Alright, so that's fun and all, but what if we want to take, I don't know, the 5th root of a number, and just take another random point, and take the 5th root of this point. And you can see we're going to get 5 very special point boys. And if we raise any of these roots to the 5th power, then we're going to get our original point. Just like last time, we're saying x to the 5th equals this number. So solve for x. And since that's a polynomial of degree 5, it's going to have exactly 5 solutions. These roots share the same magnitude, but split the circle into 5. They take the 2 pi radians in the circle and split it up 5 ways. So when you take the nth root of a complex number, what you do is you take the nth root of that magnitude and then divide the angle by n, and then shift it over n times so that you have n different roots. And here, when we took the 5th root, k is equal to 0, and then 1, and then 2, and then 3, and then 4. So the whole point of this video was just to show you the visual aspect of complex numbers. You could easily just plug values into these formulas to do your homework and not even know what these formulas mean visually. And I think that's a shame on the part of the textbooks. So yeah, that's how you do operations in the complex plane. So what's the point? Why did we have to learn how to graph and perform operations on the complex plane? Well, I've got a couple of reasons, but not every mathematical topic is going to be as practical as something like trigonometry. You probably won't need to graph complex numbers in your daily life. Alright, for one, visualizations in mathematics are very useful for gaining a more complete understanding of a mathematical problem or concept. Like how a parabola can model gravity with an object's initial distance and velocity and the acceleration caused by gravity. For the complex plane, I would recommend 3 Blue 1 Brown's video on how this infinite sum adds up to pi over 4, which uses the complex plane as a way of finding points that touch a circle with a certain radius. It's a very dense but very interesting video. There's also the case for the complex plane cementing complex numbers as actual genuine numbers. The naming in math doesn't do them any favors. After all, complex numbers aren't real numbers, mathematically so, but they are bona fide numbers, no less than any real number or whole number. There's also just math for math's sake. When you're bored, maybe you just want to draw spirals on the complex plane. The learning about the complex world creates joy for some, a feeling I hope to share. Math textbooks teach this because the complex plane sometimes crops up in calculus. And that's the end of the video, so that means it's time for another fun fact. Hitler needed to have his mustache short for wearing a gas mask in World War I. I guess after that, it kinda just grew on him. He also ruined that mustache for everybody by committing mass genocide. And as always, thanks for watching.